Thank you so much. I mean, and we're fun with time with these panels are for happen these things. So I think we can just actually continue now. We can have questions for Stuart and Paul and Adnan. And actually David is the chair. He has a lot of questions and even connections. Thank you. Let's thank Adnan first.
Okay, thank you. I'm gonna stop sharing. All right, thank you everyone. Thank you.
Okay, so we can open up for questions.
Yeah, I would have a question for Adnan. I was curious, what's the asymptotic density of the tractable circuits in the set of circuits of a given size? My guess is that they are probably asymptotically vanishing, but the argument that you would probably have that their frequency practical problems is much better than their asymptotic vanishing in the set of all circuits of a given size.
Yes, okay. So I've been mostly focused on the practical things and really building the compilers. Pierre Marquis, who I worked with in the past on this, is more into the analysis from the angles that you mentioned. So there's a lot of theoretical results on compilability and questions of the sort that you mentioned. Not the best person to answer that. But I would check the work, Pierre Marquis in Lens, France, and he's actually into this more theoretical analysis. But I am into the separation results. Separation results are a big deal because when we, practically also, when someone comes and says, let me introduce another property, what are the implications? Does it really separate circuits? That is, in a way, more practical in a certain sense, and we care a lot about this.
I have a question, but I saw Benjamin raise the hand before me, so I don't know.
Thanks, Annie. My question is for Stuart. So Stuart, you said, well, expressiveness, maybe, e.g. CF, FOL, but maybe other languages, for example, programming languages. So I'm kind of curious what your view is as far as having probabilistic versions of logic programs, or either with well-founded or ASP style, as a kind of logic to start from or to focus work around in regard to, the main topic of your talk.
Right. So, I mean, there are many attempts to combine logic programming with probability. So starting, I think, with Halperin 84 with propositional horn clauses. Nils Nilsson did some stuff on that too. The reason why I would prefer first order logic is the open universe property, right? So the idea that different worlds contain different objects, and that seems to be pretty crucial for many real world applications. So for example, in the in the monitoring for nuclear explosions, different possible worlds contain different seismic events occurring in different places at different times, and those can be different plausible explanations for the same data. And so you have to have an open universe property.
Well, I mean, I think some people have looked at how to represent open universe using declarative logic programs, and there tend to be a lot of difficulties around treatment of skolomization, equality theories, etc. And it seems a kind of a sore spot in general in the whole kind of LP, and I would include ASP as well founded in this regard realm. So, thanks. I think that's a helpful answer, and it basically points to a challenge, because I think there are a lot of advantages to working with LP and ASP in terms of understanding of tractability, how to represent various aspects of meta-knowledge and reasoning with meta-knowledge, including higher order syntax and reification and diffeasibility and some other things that are pretty weak in FOL and many people have argued are important for, you know, systems that will combine learning and reasoning. But I think you put your finger on one of the areas that really is a weakness of those approaches currently. So
So
thanks.
if I can add, actually, as I mentioned, you know, this CASP system that I talked about supports predicate set programming. So you can get model open worlds and things like that at the predicate level. It's possible in
It's interesting. The
predicate logic.
modal first order logics have historically had issues around, you know, the same objects in all worlds and how that differs, and things get complicated here. By the way, I'd like to thank Stuart for completely answering very clearly and very cogently my smart-ass question that I started this whole panel with. So
I have a question for Stuart. Continuing that, yes, I want to repeat what David has said. So, but also, Stuart, I want to put you in the same position that you're putting the deep learning people. You're telling them, well, they've made one step up, but to go farther, they'll have to do more, okay? And you're telling them how to do it. Well, I want to propose that you're in the same position, because one thing you're not doing, I mean, all the things is good, uncertainty, things, and so on and so on. But one thing that humans do all the time, in which you have not done anything, is that humans, when they are in society, they always model the thought processes of everyone else. I have in my head a model of you. I know what you know, what I know, what you know, and this goes to a very high level, because I know in my model of you that you have a model of me, okay? And this kind of gives humans fixed point operation when they talk to other people. And your one-step approach is nice, but it by far does not do this. And I think in terms of human relationships, this kind of a recursive knowledge of what the other person knows to very deep levels, and also everybody. I know, for example, my son, I have a model of him in my head, which is very rich. And in that model, I have his model of me, okay, and recursively. And this is an enormous influencer of human behavior. And I think as long as you don't address that, you're only one step up from deep learning. What do you think of that?
Well, I sort of agree. And actually in some papers I've written exactly this, that, you know, we need to look at possibly modal extensions. And the paper on open universe POMDPs actually does that in a very restricted way. And you get, you know, so with open universe actions, right? So you can tell someone, you know, tell a robot, you know, kill James Bond's uncle. Mm-hmm. Right? But if you're uncertain about who that is, then that's not a well-specified action.
Ah, yes, right.
And so you have to, you know, actually, as soon as you introduce actions into this open universe, you know, where actions can be terms, then you have issues.
But also,
so it gets quite complicated
robot,
very quickly.
But Stuart, you didn't exactly address my point. You tell the robot kill James Bond's uncle, but you have to have in your head a model of what the robot knows, okay? And you have to know that when you say that, the robot will understand because of what it knows, okay?
Yes. Yeah. I know.
So,
I was just saying that the problems start to creep in almost immediately, and then they get worse.
I think
once
true intelligence and self-awareness builds on this kind of fixed point ladders, and I think it's critical. But it's only my intuition, huh? But yeah.
Yep.
I just want to add to say deep learning people don't do that either. So.
Can I ask a question? So
sure, you go ahead. I have a question too after you.
I mean, I would argue that humans don't even think probabilistically, in the sense that if I tell somebody that Tweety is a bird, they don't say, well, Tweety will fly 90% of the time. So obviously, you know, probabilistic reasoning certainly has its value, you know, like you showed the example of being able to tell the nuclear explosion in North Korea. But in day-to-day life, I would argue that humans do not use probabilistic reasoning
Well, yeah, I'm not, this is a whole other debate. And I certainly agree that we don't use it explicitly in the sense that Tversky and Kahneman tried to test, right? You know, are we doing the right multiplications to implement Bayes' rule when you give us numerical inputs written in text? You know, so 60% of bank tellers are female and blah blah blah, right? Absolutely, we don't do that, because we didn't even know about numbers in arithmetic until fairly recently in evolutionary history. So we couldn't possibly be doing mental arithmetic explicitly in our minds, consciously, in order to do probabilistic reasoning. If we do it at all, it's done in our neurons, right? Using the neural hardware to somehow represent uncertain degrees of belief. But psychologists have actually found, so if you look at the work of Josh Tenenbaum and others, they found many, many cases where human reasoning corresponds exactly in great numerical detail to Bayesian probabilistic inference. And you know, even down to 8-month-old babies. So it's, I think there's plenty of evidence that in many situations we are doing probabilistic reasoning. And the other thing is, you know, that there is reason to believe, going back to Ramsey and Savage and others, that you just do better if you do things that way. And there may be lots of shortcuts, and I agree, default reasoning, I think of default reasoning actually as not a logic, but actually a phenomenology of inference. And probabilistic reasoning systems can exhibit exactly the same phenomenology as default inference, right? If you're doing MCMC, the first thing you want to do, the first guess you make about what the world is, you should guess the most likely one first, because then you'll converge fastest to the true probability. So you get exactly default inference, but as a phenomenology, not as a logic. So, okay, I'll stop there.
Can I ask a question? I have a question for both Stuart and Adnan. Well, actually, let me just start to say, right, I just love this language, right, Stuart showed. They're just so beautiful. We see that example. I know he has many examples. And then this, you know, Adnan had this Boolean circuit compilation that's just so beautiful. And I know he has also many applications. But I had one question, I mean, really for both of you, because I thought, so one thing, I mean, they could do this, right? I think both of you could really something really deep understand, and the semantics really getting something sorted out. But I never quite understand this origin neural model. I mean, every time I try to read it, I have some idea. So today I finally somehow thinking, oh, that's your path of generation, so allow you to have this uniqueness, so you can do the efficiency. So I finally thought, okay, I really got that somehow. But then I saw Adnan's talk. I saw other versions of talk in the last couple of years, actually. They were all beautiful and different. But then he was saying, well, right, he doesn't, I mean, these things appear to be different, unique, coming, you know, from different paths, and he actually wants to remove redundancy and somehow make them to be the same, to recognize they're the same, even though they generate, maybe, I don't know how they come from differently, right? So I don't know how to reconcile this, or maybe I'm just misunderstanding all those.
I mean, is there some connection between, between this Adnan's sort of uniqueness and looks like my picture is frozen. And between Adnan's uniqueness and this uniqueness, I'm not sure. I think at a high level, possibly, right? Because it's Adnan wants to avoid having to, you know, in doing the recursive computation on the tree, he wants to avoid introducing, you know, combinatorics, and so he specifies these requirements such that there's still a linear time recursive algorithm for computing, you know, the weighted sum of satisfying assignments or whatever it might be. And I think that's a very elegant idea. I don't know, it's a sufficient condition, but is it necessary? I'm not sure. But yeah, we're trying to avoid. So this is really I mean, this definition is in the semantics for us.
Exactly.
Right? Just to avoid having to define the probability of a possible world as the sum over all possible ways of generating it. Now you could do it that way, right? It's just that you would have a pretty opaque semantics right? And you just have to sort of take it on trust that that sum, that you know, someone could work it out if they were very clever, whereas this makes the semantics trivial to understand. So I just felt that, you know, and we introduced it to overcome exactly this problem of multiple ways of generating the same world.
Sounds like Bob has a question, maybe?
Oh, well, maybe
yeah,
Adnan didn't answer yet. Can you, because that was a question for both of them. Thank you, Stuart. Thank you.
Sorry.
To reinforce my little understanding. I wonder what Adnan thinks, how is this related to?
Yeah, I agree with Stuart. I think, well, the notion of uniqueness is a broad one. And in his case, it's being applied at the semantic level. And for us, it's at the computational level. We're trying to basically save computation. So different levels of basically thinking about that notion.
Okay, thank you very much. Sorry.
Okay, Bob, you have a question?
Hey, thank you. I want to go back to this question that's come up several times, I think, and that's whether probability is enough to deal with default logic or default reasoning. Suppose you're crossing the street and most of the time there's not a car in the road, so you just walk, you know, blindly across the street. So, and the probability is you'll be safe, but the utility of being wrong is so high that most people would look to see whether or not a car is coming. So basically, what default reasoning gives you, and what probabilistic reasoning does not give you, is it brings in the possibility of incorporating utility and significance of making a decision. So I'm wondering whether people who have concerned themselves with probabilistic reasoning have incorporated utility and decision theory as well.
Well, I think of decision theory could only exist on the basis of probability theory. So
yeah, but what about default reasoning incorporating decision theoretic utility considerations?
I mean, default reasoning just compiles the combination of probability and utility into a decision and says, you know, if you don't see a car, cross, right? And that's fine. And, you know, so information value theory will tell you whether it's worth looking, right? So it used to be that if you didn't hear a car, you could cross, because if you didn't hear a car, then there wasn't a car. But now with electric cars, if you don't hear a car, there could still be a car. And actually that probability is increasing every year. So the people who don't update their default rule are going to be dead. So that's where evolutionary computation comes in.
Okay, but the thing is that you suggested, I thought, that you could do default reasoning through probability alone. And now I think you're suggesting that you would need to combine it or introduce it as an additional feature. Is that right?
Yeah, so what computations you do, I mean, so I wrote a whole book about this back in 1991, right? So what computations you do is dictated by the value in terms of improving your decisions. And so yes, you need to take into account utility in choosing what variable to sample first, for example. And that you know, people have shown how to do this in decision diagrams, for example.
I had a quick question. We're getting right near the end, but I had a quick question for Paul. A general sort of question is so what did we learn from your exercise, and how the machine learning is learning theorems? Why does that work to the level it does? I guess is my question. Is it learning structures of proofs? Is it learning, what's it learning to make that work? What of the structure is it taking advantage of? How is it doing this?
Yeah, let me start by answering when it doesn't work. For instance, in one of my practical projects at this time, we are playing with molecule graphs, for instance, in some kind of symbolic representation, and we want neural networks to learn toxicity, which of them is toxic, which of them is not. And when there is no structure or there is very, very little structure that correlates those elements, things will not work very well. Definitely not to the point where it works with this synthetic artificial data, because logic is you know, logical. So because of that, it works really well, even if it's not a finite valued logic. Intuitionistic logic doesn't have a truth table, and it still works and is p-space complete. Now, it doesn't work as well as on linear logic, because the structure, the correlation via the Curry-Harvard, the isomorphism between the, let's say, sizes of the types versus the sizes of the proofs, which are the lambda terms in this case, is not one-to-one. It can actually go exponentially higher either way. One of them could be exponentially bigger than the other. And in that case, the acid test there would be how it works with very large or very artificial examples, especially the human-made ones. And that's subject of future work here.
Thank you. I hadn't thought of that. That makes sense. Makes good sense. Thank you.